Now we talk about section 2.4. Section 2.4 covers the complex numbers. The complex numbers encompass the real numbers, and we will move forward with this number system. So previously, we've been able to solve equations like x squared minus 4 is equal to 0. We could solve that by moving 4 over and then taking the square root of both sides. So we get x is equal to plus or minus the square root of 4, which is equal to plus or minus the square root of 2. And we get two answers for that. And these are both integer answers and therefore real numbers. The problem becomes if you want to solve something like x squared plus 4 equals 0. Now, if we subtract 4 from both sides, we'll have x squared is equal to negative 4. And this is a problem because squaring a number always will keep it positive. And yet this is a negative number. So if we solve this, we get x is equal to plus or minus the square root of negative 4. And this is not a real number. And this leads to implications when graphing and such. So to solve this, we needed a new number system. And to do that, we had to come up with the imaginary unit. Okay? So the imaginary unit I. Okay? Now, by definition, I is defined to be the square root of negative 1. And I squared, then, is defined to be the real number negative 1. And this is helpful for us in simplifying square roots. So, for example, if we have the square root of negative 4, we can alleviate this not a real number problem by switching into the imaginaries. Okay? Remember that the square root of a times b can be written as the square root of a times the square root of b. And we'll use this fact to simplify this number. We could write this as the square root of negative 4 is the square root of negative 1 times 4. Now we have two things multiplied together. So this can be written as the square root of negative 1 times the square root of 4. The square root of negative 1 then is defined to be I. And we can simplify the square root of 4 as 2. Which, since multiplication commutes, we could really write this as 2 times I. And this gave us a simplification. We can go a little further with it. If we had the square root of negative 24, remember, we'll split this up as the square root of negative 1 times 24. And then we'll take the prime factorization of 24 because we want to simplify this radical. 2 goes into 24 12 times. 2 goes into 12 6 times. And 2 goes into 6 3 times. So we can split this up. Square root of negative 1 times the square root of 24. This is just I by definition. And we can simplify the square root of 24 by pulling out, there's one group of 2's, so we can multiply that by 2, and then everything that doesn't have a grouping has to go back and be multiplied back together and put underneath. So in the end, writing this, commuting this, we'll get 2i times the square root of 6. And then that's the way that the imaginary unit is helpful for us. Now, when we mix the complex, the real numbers and the imaginary numbers, we get the complex numbers. So, definition, a complex number comes in the form a plus bi, where a is known as the real part, that is from the real numbers, and b is the imaginary part. So, for example, it could be something like 3 plus 4i, 1/2 minus 3/4 I. These are examples of complex numbers. For example, 1/2 is the real part, and negative 3/4 is the imaginary part. Okay. So complex numbers have two parts, the real and imaginary, and because of that, we can actually graph them in the complex plane. The complex plane looks exactly like the Cartesian plane or our xy plane. Except the x-axis is known as the real axis, and what we consider the y-axis is the imaginary axis. So, for example, if I had to plot the complex number 3 minus 4i, I would have to go over 3 units in the reals, and then up 4 in the imaginary. This would be the complex number a, which is 3 minus 4i. We could do negative 4 minus I, and what we'd have to realize here is that that's a negative 1. So we could go over 4 units in the real, and then drop down 1 in the imaginary, and this would be the imaginary point B, representing the number negative 4 minus I. We could also talk about graphing the number 3i. This is a purely imaginary number, but we could always write it as a complex number by thinking about it as plus 0. So this would say I will go nowhere in the real part and up 3 in the imaginary. This is the point C, 0 plus 3i. But the complex plane also encompasses the real numbers, so I could just graph the number 5. And the way we could think about that then is that I have no imaginary parts. It's purely a real number, but here it is written as a complex. So that would mean I would need to come over 5 in the reals and then go nowhere in the imaginary. So this is D, the number 5 plus 0, I. So graphing them is very simple, and now we just need to talk about how to add and subtract them, complex numbers. So, definition. We will add and subtract complex numbers. So let's say we have two complex numbers. The first one, let's call it a plus bi. It will be in this form. And I want to add to it a second complex number. Let's just call it c plus di. All this amounts to is collecting like terms. Okay? So we would like to distribute this understood 1 between each of these. And since we're just adding, everything will be positive, so this will just be a plus bi plus c plus di. I can collect the real parts, which would be a plus c. Remember, these will be just numbers, so we can add them together. And then I will add to it bi plus di but notice that there's a common factor of an I here and here, so this will be the same as a plus c plus, I'm going to factor out that I. I'll factor it out to the right, and that would leave behind b plus d, I. It's probably easier to see in an example. So, for example, if I have to add 3 minus 4i plus 2 plus 5i, well, this number is going to stay the same. There's just a positive 1 that goes through. So this is 3 minus 4i. And then, again, a positive comes through here, which is just 2 plus 5i. Which now, collecting like terms, 3 plus 2 is 5. And negative 4i's plus 5i's leaves me with a positive 1i, which you could just write as 5 plus I. Now, if we're going to subtract numbers, complex numbers, we have some other problems we have to deal with. Let's just jump with the example. So if I have negative 5 plus 7i minus 11 plus 2i. So here's our subtraction. Again, to drop the parentheses, I'll just distribute this through. So negative 5 plus 7i. The difference is here, just like when we're subtracting polynomials, we have to remember to distribute the negative through. So this will become positive 11 minus 2i. And now we can collect like terms. Negative 5 plus 11 is 6, and 7i minus 2i's is plus 5i. So adding and subtracting complex numbers is really simple. And so is multiplying them. For example, let's say I wanted to take 4 times the complex number 2 plus 5i. Again, this is just a distributing exercise, and so 4 times 2 is 8, and 4 times 5 is 20i. So there's nothing too difficult here. Even if we want to multiply 2 numbers, it gets a little more complex, but not difficult. So here I'm multiplying the first complex number by the second complex number. And again, this is just a matter of distribution, and we can think about that as foiling. So here we go. 4 times 2 is 8. 4 times negative 5i is negative 20i. Then 3i times 2 is plus 6i. And lastly, 3 and negative 5 are negative 15. I times I is I squared. Which we can combine these like terms. So we'll have 8 minus 14i minus 15i squared. But there's a problem here. Notice that when we were multiplying above, we multiplied a number by the complex and we came out with a complex number. The same thing happened when we were adding or subtracting. Add 2, get a complex number. Subtract 2, get a complex number. And so we need to write this also in the form of a complex number. And here is where we will use the definition of I squared. Now remember, by definition, I squared was equal to the number negative 1. Okay. So this is 8 minus 14i minus 15 times now negative 1. And now we'll simplify our signs. We have a negative 15 times a negative 1 becomes positive 15. And now we can combine these like terms. 8 and 15 is 23 minus 14i. Let's do another example. Okay. 3 minus 4i times 2 plus 3i. Okay, let's begin. We know we're going to have to FOIL. It's multiplying. It's just distributing. So 3 times 2 is 6. 3 times positive 3i is plus 9i. Negative 4 times positive 2 is negative 8i. Then negative 4i times positive 3 is negative 12, and I times I is I squared. We can collect like terms. So 6 plus I minus 12 times I squared. And we want to write this as the complex number a plus bi. So we'll have to remember that I squared is negative 1. So this becomes 6 plus I, and now a negative 1 times a negative 12 is positive 12, which is equal to 18 plus I. So notice by multiplying by I squared, we were able to remove any imaginary numbers and come back into the real numbers. And that will be helpful for us as we move forward with dividing. First, let me tell you what the complex conjugate is. So for any number a plus bi, its conjugate is a minus bi. So you keep the real parts the same, the imaginary parts the same, and just like any other conjugate, you switch the addition and subtraction sign. So for example, if we have negative 3 plus 4i, then the conjugate is negative 3 now minus 4i. Okay, and how that could be helpful to us is when we divide. Dividing complex numbers so we're dividing complex numbers. Say, for example, a plus bi divided by c plus di. Again, we will want the result to be a complex number, so it needs to come in the form of something like g plus hi. Okay? That is, there is no imaginary units in the denominator once we've finished. So in this way, I liken dividing complex numbers to rationalizing a denominator, because when you rationalize the denominator, the goal is to get rid of the radical. When dividing complex numbers, the goal is to remove the imaginary unit from the denominator. And the way we do that is using the conjugate. So, for example, let's take 2 plus 5i and divide that by 4 minus I. Okay? So this is our division problem. We have an imaginary unit down here in the denominator, and the goal is to get rid of it. So the way we do that is that we can multiply the conjugate, and that in this case is 4 plus I. But remember, we have to multiply by 1, so we have to multiply 4 plus I over 4 plus I. And it might be helpful then to think about these using parentheses. So here we go. Now we will just FOIL up top as we've done before. Okay. So foiling, 2 and 4 is 8, plus 2i, plus 20i, plus 5i squared. 20i plus 5i squared. Down below, we'll FOIL as well. 16 plus 4i minus 4i minus I squared. And now we can collect like terms. So we'll get 8 plus, now this becomes 22i, plus 5 times, but remember I squared is negative 1. We can divide that by 16 plus, well, 4i minus 4i is 0i, which is just 0. And then minus, and I squared is negative 1. So we have that this is 8 plus 22i, now minus 5, over 16 plus 0 plus 1, which is 8 minus 5 is 3 plus 22i over 17. And we've accomplished our goal. There is no imaginary unit in the denominator. And if we want to write it in the form a plus bi, well, we can just split this fraction up. Take it to 3 over 17 plus 22 over 17i. Either of these are equivalent ways of writing. We also have to talk about the powers of I. I is kind of an interesting number, so let's check out why. Definition. The powers of I. So, by definition, we know that I is equal to the square root of negative 1, which is equal to just I. We also know I squared is equal to negative 1. But what happens if we were to look at, say, I cubed? These we have by definition. So let's use these to determine what I cubed would be. So I could rewrite I cubed as I squared times I. And if you want, you can think about that as I to the first. I can do that because when we're multiplying with like bases, you would add the exponents. But now what do we have? Well, I squared, by definition, is negative 1. And then we multiply that by I to the first power, which is just I. So we get the result that I cubed is equivalent to negative I. We could look at I to the fourth, and we could write that as I times I. I could do it 4 times, or I could say, how about I squared times I squared? We do that because we know that I squared, by definition, is negative 1. So if I take negative 1 times negative 1, what I get is the real number 1. Let's continue. This is a nice number. This is our multiplicative identity. So what if I looked at I to the 5th? Again, I want to rewrite this in some powers of I that we already know. How about I to the 4th, because that's equal to 1, times I to the 1st. Then we'll get negative 1 times I to the 1st is just I. So I to the 5th is equal to, I'm sorry, not negative 1. This is positive 1, because I to the 4th is positive 1, is equal to just I. Continuing, I to the 6th has to be I times I. Let's look at the 4th power and the 2nd power. So this will give us the positive 1, I to the 4th is positive 1, and I squared is defined to be negative 1. So I to the 6th is equivalent to negative 1. And I hope you see a pattern building here. I would anticipate then that I to the 7th should be equal to negative I. So let's look. Again, comparing powers of I. Let's take I to the 4th because it's equal to 1, and then I cubed. So I to the 4th, as we've said, is 1. But I cubed from above was equal to negative I. And so, yes, I to the 7th is equivalent to negative I. So I to the 8th, again comparing powers of I, would be I to the 4th times I to the 4th, which is a positive 1 times a positive 1, which is just equal to positive 1. I hope we can see a distinction between here. What's happening here is that these numbers are cycling through. And so imaginary numbers are known as cyclic. We will be able to reduce them to one of these forms, all powers. So let's see how this might work. Okay. So for example, I to the 18th. Well, if I think about this, I'd like to think about this as I to the 4th times I to the 4th times I to the 4th. So this is 12 plus I to the 4th, which is 16, times I squared. Because when multiplying with like bases, you'll add the exponents. So 1, 2, 3, 4. 4 times 4 is 16, plus 2 is 18. The reason why we do that is because we know that this is equal to 1, this is equal to 1, 1, and 1. And then by definition, all we're left with is I squared, which is equal to negative 1. An easier way to see that might be, because fourth powers of I are equal to 1, we want to know how many times does 4 go into 18. So 4 goes into 18 4 times, hence 1, 2, 3, 4. 4 times 4 is 16. And I subtract, and the remainder is 2. And that's exactly what we have here. So the power of 2 corresponds to negative 1. Let's try one more. I to the 35th. Now I could write this out multiple different times like I did here. It's going to get long. So what I might consider is just how many times does 4 go into 35? Well, 9 times 4 is 36, which is too big. So 8 times 4 is 32. Subtracting, I'll have a remainder of 3. So this means that I to the 35th will have the same value as I cubed because of the remainder. And from above, I cubed is equal to negative I. Okay, I hope that's a good refresher for you about the complex numbers and how they work. We will, of course, be using these to solve quadratics and various other topics. Send me an email if you have any questions.